Good evening, my dear students. Welcome to ACE Engineering College YouTube live session. Myself, Sujath Ali Khan, Applied Physics faculty from ACE Engineering College. As a part of series of lectures of Applied Physics, today I would like to explain chapter 5, means unit 5, in that we are having lasers and optical fiber. In our previous class, I discussed some important questions related to lasers. So I would like to continue few more topics, means in that I'm going to explain about different lasers. So what are the different lasers that I'm having? See here. The different lasers that I'm going to explain. So in that ND-YAG laser. What is this? ND-YAG laser. Okay. In our previous class, I explained about ruby laser, that is a solid state laser. ND-YAG laser also solid state laser. In this, ND means neodymium. What is this? Neodymium, yttrium, aluminum, garnet. Okay, so neodymium doped in the place of yttrium ions. So today I am going to explain about the ND-YAG laser, and also I am going to explain about the one more laser, that is helium-neon laser. One more laser I am going to explain, that is semiconductor laser. What is this? Semiconductor lasers. So these are the three topics that I am going to explain today. And apart from these three different lasers, I am going to explain some applications of lasers. What? Some applications of lasers. Okay, so helium-neon laser, ND-YAG laser, and semiconductor lasers. So these are the lasers that I am going to explain. Okay, apart from this one, I am going to explain some important applications of lasers. Okay, so now I am going to explain about ND-YAG laser. What is ND-YAG laser? It is a neodymium. What is this? Neodymium doped. What is this? Neodymium doped in yttrium, aluminum, garnet. What is this? ND means it is a neodymium. Okay. Next, Y means yttrium. Okay. A means aluminum. Okay, O2 means, here O2L is nothing but, it is a garnet. Okay, so what we are going to do here in this ND-YAG laser, as we have done in ruby laser. What we have done in ruby laser, we doped Cr+3 ions in the place of aluminum. What we do? We doped Cr+3 ions in the place of Cr+3 ions in the place of aluminum ions. Now here we are going to dope Nd ions, which are having +3 charge. Okay, +3 ion doped in the place of yttrium. Few of the yttriums are replaced in the place of yttrium. We doped with neodymium ions. Okay, so what is that? I am going to explain here. So it was first demonstrated by J.E. Jusek in the Bell Laboratories in 1964. In the year of 1964, he is the scientist, first one. Jusek is the first scientist who demonstrated about the ND-YAG laser. Okay, so what is this ND-YAG? In this, what will happen? Neodymium ions are replaced with what? Yttrium ions. Not complete yttrium ions are removed. Few of the yttrium ions are replaced with Nd+3 ions. How much? 0.725. How much? 0.725% weight of the rod. Whatever the rod, it is a solid state laser. No? So whatever that rod is having, from that 0.725% of neodymium ions are replaced in the place of yttrium ions. Means yttrium ions are removed. In that place, neodymiums are doped. Okay, so that is called neodymium doped yttrium aluminum garnet laser. neodymium doped yttrium aluminum garnet laser. It is a solid state laser. Okay, it is a 4-level laser. Like as ruby laser, it is a 3-level laser. It is a 4-level laser. So what is a 4-level laser? So 4-level laser means we will have 4 different energy levels. Okay, so this is E1 level, it is E2 level, and it is E3 level. Next, this is E4 level. Now from this ground state, these atoms are going to excite here by absorbing some sufficient amount of energy. Okay, the lifetime is very less, 10 to the power of minus 8 seconds here. So now we have to allow in that second level, that is called metastable state. What is this? Metastable state, where we can allow these atoms first to stay for some time in order to achieve the population inversion. Now this is metastable state. This state is considered as ground state. Okay, so here we are going to maintain more number of atoms for longer time. So when you are able to maintain population inversion for a longer time, the output laser should be of continuous form. Where in the ruby laser, it is a 3-level laser, so it is not that much possible to maintain the population inversion for a longer time. Here we can maintain population inversion for a longer time. This is 4-level laser. Okay. Now I am going to draw the diagram here. See here. Neodymiums are providing the lasing activity. What is this? Neodymium ions are providing the lasing activity. In the case of ruby laser, who are providing the lasing activity? Chromium plus 3 ions are providing the lasing activity. But here, who is providing the lasing activity? The doped elements only. So remember, my dear students, doped elements are only going to produce the lasing activity. In that ruby laser, we doped with chromium plus 3 ions. Here in the NdYAG laser, we are doped with Nd plus 3 ions, neodymium ions. So neodymium ions only providing the lasing activity. What is this lasing activity? Who is providing this one? Okay, so chromium. It is same as chromium ions in the ruby laser. It is a 4-level laser. Now I am going to construct the NdYAG laser. First, we should have one elliptical shaped cavity. See here, what is this elliptical shape? How many focus points are there? Elliptical shape, it is having one focus point and it is also having one more focus point. This is one more focus point. Here it is one more focus point. So that is the importance of elliptical shape object or body. It will have 2 focus points. How many focus points it will have? 2 focus points. Okay. Now, so it is a elliptical shaped body. Now I am going to take see here, it is elliptical shaped cavity. What is this elliptical shaped cavity? It is having how many 2 focus points? This is one focus point. It is one more focus point. So this is focal length. What is this? It is one focal length. And what about this one? It is also one more focal length. How many focal lengths it will have? Because it is having 2 focus points, this elliptical shaped body will have 2 focal lengths. Now what I am going to do? I am going to place in one focal length, I am placing this NdYAG rod. What I am placing? NdYAG rod. In one focal length, what I am doing? That rod I am placing. Next, another focal length, I am using, what is this? A flash lamp. What is this? A flash lamp I am placing. This flash lamp will be either it is xenon or krypton. You can use either xenon flash lamp or you can use krypton flash lamp. Where you are placing this one? You are placing that where you are placing? In the one of the focal length point. So one of the focal length point. Now I am connecting one capacitor here. So apart from one battery with variable resistor, so this is the construction of Eng laser. Okay, so simple thing what we need here, elliptical shaped cavity. So what it is having? It is having two focus points. So two focus points means two focal lengths we will have. So in the two focal lengths, one of the focal length we are placing the Eng rod. Another focal length what we are placing? Flash lamp for pumping of the neodymium ions. We have to excite the neodymium ions to achieve the population inversion. So pumping for pumping purpose we are using this flash lamp. Where it is kept? It kept one of the focal lengths of elliptical shaped body. Okay, so that is connected to power supply and also with the capacitor. Okay, the two sides of this one side you are having one mirror. What is this? It is a mirror M1. It is less than 100, it is a 100% reflector. 100% reflector. It is 100% reflector. The other side what you are having? It is one more mirror. It is mirror M1 and it is mirror M2. What is this? Partial reflector. So what we are having? Elliptical shaped cavity having two focus point. One of the focus point means one focal length we are placing Eng rod. Another focal length we are placing the flash lamp, xenon or krypton flash lamp. So that we are connected to a power supply. So two sides what we are having? Mirrors. One side fully reflector, the other side you are having partial reflector. So when we are giving certain amount of energy, what happened? See here, this is the animation that I have done. What it is? Elliptical shaped cavity. Elliptical shaped cavity. It is having one of the focal lengths. What it is? It is one focal length. It is one focal length. And one more focal length, what it is? It is one focal length. This is one more focal length. Okay. So I place a flash lamp in one focal length and another focal length what I am doing? I am placing Eng rod. Now, so here what we are having? A mirror M1. Here I am having mirror M1 and the other side I am having mirror M2. It is fully reflector, it is fully reflector. It is partial reflector. What it is? Partial reflector. Okay. Now what I am doing? I am connecting the power supply. It is a battery power supply and it is a capacitor and it is a resistance. So this is the construction of a Eng rod. Okay. So how the lasing action is going to take place in the Eng rod? Now I am going to explain. See here. So see what is the what is this one? See. So it is an energy level diagram. Okay. So this is a ground state energy level 1. Okay. This is energy level, pump level. Pump levels, two pump levels. Now here we are presenting here neodymium ions. What are these? Nd+3 ions. They are present in the ground state. These are the neodymium ions present in the ground state. So the flash lamp, we place a flash lamp in the one of the focal length. Where we place? We place one flash lamp, one of the focal length of a elliptical shaped cavity. Okay. So that flash lamp is generating some light. So that light is having two ranges. So one is having 0.73 micrometer. That is having 0.73 micrometer. Next, one more wavelength will be there, that is 0.8 micrometer. Okay. So when 0.8 micrometer is there, it will excite to this level. And 0.73, the atom will be excited to this level. These are pumped, means they are the excited levels of the neodymium ions. Those are called pumping levels, pumped levels. Okay. So next, we know that these excited neodymium ions will not stay in the excited level for a longer time. The lifetime is very less. You know what is lifetime? The amount of time that the ions or atoms are present in that particular state or level is called lifetime. If stay there more time, means their lifetime is more. If they are staying for a less amount of time, means their lifetime is very less. So excited level atoms or ions will not be stay for longer time. Their lifetime is very less. So they are going to allow in the one more state is called upper laser level. Upper laser level. This is also called metastable state. It is also called metastable state. Why we are using metastable state? Because the most important criteria for achieving the lasing action is, first we have to achieve the population inversion, then you have to achieve the stimulated emission. So these are the two things that we have to achieve in order to get the lasing action. First we have to achieve the population inversion, then we have to do lasing stimulated emission. Then only laser emission will take place. The first one is we have to achieve the population inversion. How we will achieve the population inversion? Because we know that excited neodymium ions in the pumped level will not stay for a longer time. So we have to allow them to one more state called metastable state, where their lifetime is somewhat more. So they will stay for more time, so that we can make the more number of atoms in the upper means metastable state. When we are getting more number of atoms in that particular state compared to the ground state, then you achieve the population inversion. We know that having more number of atoms in the higher energy level than its lower energy level is called as population inversion. So how we are going to get the population inversion here? By getting more number of atoms in the metastable state than the lower state. So metastable state is a state where the atoms will stay for more time, so that we can get the population inversion condition. So first, this is the ground state, okay, ground state, E1 state. So these are the pump level. Next means E2. E3 and E4. Next it is E2. Next it is E1. Now, once the neodymium ions are excited to higher energy level, these ions won't stay for longer time. The transition of these neodymium ions will take place from this level to and also from this level. So here we are going to get some emission of photon, that is non-radiative emission. What it is? Non-radiative. When the transition of neodymium ions takes place from the pumped level to metastable state, so the energy is non-radiative emission. Okay. So once the atoms are reached to this metastable state, more in number, if you reach more in number, so the number of ions here, if they are more, for example, let us take N2, for example, here number of atoms are N1. If you achieve the condition N2 is greater than N1, means you achieve the population inversion. Okay. Next, what happened? So one of the photons are going to emit to ground state, and this neodymium ions is coming down from upper level laser to, so one more laser level, lower laser level. So when they are coming, they are going to release the photon. These photons are going to come out from the mirrors. The mirrors are there now, that we are having mirrors now. So they will reflect from the mirror. Okay, so when they are reflecting from the mirror, what happened? They will going to have an interaction with these neodymium ions. When they are interaction with this one, what happened? They will cause stimulated emission. So this ion is going to come down, and this is going to release the energy in the form of coherent. Coherent form of energy is going to release. See here, this is the diagram. So what is the use of elliptical shaped cavity? Why we use here elliptical shaped cavity? Okay, the elliptical shaped cavity having one good characteristics. What is that characteristic? So whatever the light, for example, it is a light, it is a light. No? So let us say, so it is a neodymium ion. What it is? Neodymium ion. It is a neodymium ion, plus 3 ion. Okay. Now, when light comes to here, it will interact with this ion. Light is going to interact with that ion. When it is interacting with that ion, what happened? Okay, it will directly interacts. Sometime light comes to here in this direction, and it will reflect back, and also it will interact with the neodymium ions. Or once, for example, light is emitted from here. It comes towards the mirror, and it will reflect back here, and it will come to interact. Means, compared to ruby laser, neodymium means neodymium agnum laser, Nd:YAG laser. So what is the advantage here? In ruby laser, flash lamp we use now. Whatever the light is emitted from the flash lamp is having interaction few photons only. But here in the case of neodymium Nd:YAG laser, every photon emitted from the flash lamp is going to come towards the one other focal length. Whatever the light emitted from the one of the focal length, it is going to reach to the another focal length where we place the Nd:YAG rod. Means every photon has to reach the other focal length. So that is the nature of a elliptical shaped cavity. Means every photon emitted from the flash lamp is going to interact with the neodymium ions placed in the second focal length. So that is the important. So that means we are having more laser gain, means more amplification, more interaction of photons will be there. So that we are going to get amplification of photon. So amplification of photon will be done more easier than the ruby laser here. Okay. So that for that purpose only here elliptical shaped cavity is used. See here. So first, these are the neodymium ions. What are these? These are the neodymium ions. It is also neodymium ion. Okay. So these dymium ions are interacted with 0.73 micrometer, and so what happened? See here. One more time. See here. See here. Means one photon of 0.73 micrometer, one photon of this much 0.8 micrometer. So when they are interacted, okay. So here what we are having here, it is a neodymium ion, and it is also neodymium ion which are present in the ground state. So we are having two photon. One is 0.73 micrometer. It is what? 0.8 micrometers. Okay. So 0.8 micrometer they are interacting. It is having shorter wavelength. So this neodymium ion will excite to more pumped level. Next, it is having excited to lesser, means it is also excited to E4 level. Okay. So because it is having 0.8 micrometer and it is having 0.73 micrometer. So shorter wavelength and longer wavelength. Shorter wavelength will have more energy. So it is excited to more upper pump band. So it is 0.8 means longer wavelength. So having less energy. So it is excited to lower pump band. So this is the case of excitation of neodymium ions by absorbing these wavelengths. Where these wavelengths came from? They came from the flash lamp we placed at one of the focal lengths of elliptical shaped band. What is the flash lamp we use? Either you can use xenon flash lamp or you can use krypton flash lamp. So that flash lamp is providing these two wavelengths, one is having 0.73 micrometer, another one is 0.8 micrometer, so that the neodymium ions will absorb these two different wavelengths of light and they will excite to two different pumping bands, E4 and E5. So we know that these neodymium ions will not stay in this particular level for longer time. So they are going to come to this level. So when they are coming this way, they are giving non-radiative transition. Okay. So after that, they are going to come down here. Who is going to come? These are the neodymium ions coming from this E5 band and also from E4 bands. They are coming from E5 band and also from E4 band. So now we are going to get more number of atoms here. We are going to have more number of atoms in this particular level. We are having more number of atoms. Means compared to this E3 lower laser, it is called lower laser, it is called upper laser. It is upper laser and it is a lower laser. So here we are having more number of atoms. Say here number of atoms are more compared to this one. So after that, what happened? One of the atom is going to, neodymium ion is going to come down to the ground state spontaneously. So transition of neodymium ions takes place from this E5 level and E4 level to the E3 level, upper laser level. So they will come to this level. So while they are coming, they are giving the radiation called non-radiative transition. Okay, once they enter into this E3 level, upper laser level, means metastable state. So they will stay for some time, means the lifetime is more. So population inversion we can achieve. Once we achieve the population inversion, these atoms are going to they are not going to stay here for more time. So some of the atoms are coming down spontaneously. When these atoms coming down spontaneously, for example, this is a spontaneous emitted photon. So for example, see here, what we are having, elliptical shaped body, no? So here we have flash lamp. What we are having? Flash lamp. Here we are having rod. What we are having? This is rod. Okay. So we got one photon, spontaneous photon. What is this? Spontaneous. It is moving towards the partial reflector, M2. What is this? Partial reflector. Okay. So this partial, it want to come out from the partial reflector, it won't come out because its energy is very less. Now it reflect back. It reflect back and interacted with the neodymium ion present in this level. So this, for example, it is coming down, and for example here, for example, it is coming down, okay, and it is a mirror, okay, it is reflected back, and it is interacted with this atom, neodymium ions. So a neodymium ion already having the photon, now it is going to come, it release two photons in coherent. These two photons with more energy try to come out from the mirror. Okay, but their energy is not sufficient. Once again, they will reflect back and going to have interaction with the two more neodymium ions present in this upper laser level. Now they are causing two more atoms to de-excite to this lower laser level. Okay, so when there are two atoms are coming down to the lower laser level, how many photons will emit here? 4 photons. Now these 4 photons are going to move in a coherent form in one particular direction with more power compared to single photon, compared to 2 photon. Now you are getting 4 photon in one particular direction, not different direction. They are moving in one particular direction. Therefore, the total amplitude, the total intensity or total power of this photons, group of 4 photons will be more amplified. So this 4 photon tries to come out from the mirrors, but they are not going to have sufficient amount of energy. So they are going to reflect back one more time. So they are reflecting back and they are interacting with how many number of atoms present in the upper laser level, means metastable state? 4 neodymium ions. Now the 4 neodymium ions are going to come down. How many photons now we are going to get? 8 photons. Now we are going to have the energy of 8 photons together, means the energy of the photon is amplified. So like this means lasing action. This amplification of photon is continuously takes place until these photons have sufficient amount of energy, then they will come out from the partially coated mirror. That is M2 mirror, that laser beam will come out as a intense coherent form of light. Okay. So one more time I am explaining here. See students, it is a low energy level E1. It is one more level. First, I am having one neodymium ion. What is this? Neodymium ion. So I am giving certain amount of photon. Who is giving? Not I am not the giving. Who is giving? The flash lamp. Xenon or krypton flash lamp is giving two wavelengths. In that, this is the how much? 0.73 micrometers. Okay. So when it absorbs, it is excited to one level, that is, for example, E5 level. What is this? E5 level. Now I am having one more neodymium ion here. So now the xenon flash lamp is giving another wavelength of light. So how much it is? 0.8 micrometer. Okay, so when it is absorbed, so 0.8 is more wavelength than the 0.73. More wavelength means lesser energy. Means this photon is of lesser energy interacting with this neodymium ion present in the ground state. So less energy means it absorbs less energy, so that it will excited to lower excited level, lower pumped level. So that is E4 level. So these are called pump levels. What is called? Pump levels. Okay, so this neodymium excited to here, and this neodymium excited to here. So these are the pumped levels or excited level. So the lifetime is very less. Okay, they will not stay there for longer time. So when the ions are not able to stay for longer times, we can't achieve the condition called population inversion. So our intention is to make the more number of ions in the higher energy level. For that, what we are having, one level is called, this is upper laser level. Okay, that is also called metastable state. Metastable state. Okay, so what it is? E3. Next we are having one more level, E2. So lower laser level. Two levels, upper level laser, lower. Now these are the pump level, means excited state. These ions won't stay for a longer time, so we have to allow them to enter into the metastable state, where we can make them to stay for more time. So this ion is also going to enter here. So these are the transition takes place from the pump level to metastable state. When they are coming to from this level to this level, they will radiate some amount of energy, that is non-radiative emission. Non-radiative emission. Now this is upper level is also called metastable state, where the atoms or ions are going to stay for more times. Okay, so when these ions are staying for more amount of time, we are going to achieve the population inversion. What we achieve? Population inversion. So after the transition takes place from pump level to metastable state, now transition from this upper level laser to lower laser level. For this atom is coming down spontaneously. Few of the atoms are going to come down to the spontaneous emission, and they are going to release some amount of energy. So ordinary photon, that is not laser, ordinary photon emission takes place. Now this photon tries to come out from the mirror. What is this? Mirror. Okay, mirror M2. But this photon won't come, unable to come out from the mirror, because its energy is not sufficient. It will reflect back and interacting with this neodymium ion. Neodymium ion already having one photon inside. So now this reflected photon, mean feedback photon, is interacted with the neodymium ion. Now this neodymium ion coming down to the ground state. This lower level, lower laser level, not ground state, lower. These two photons, how these two photons? In coherent form, means the photon energy is more, okay, compared to this single photon. Okay, now these two photons are incoherent, so their energy is amplified. Now these two photons tries to come out from the another mirror here. What we are having? Another mirror M2. Okay, so they will reflect back and interacted with how many photons? How many ions? Two ions, because two photons are there. So I already told you in my first class, one photon can interact with one atom only. Now how many photons are there? Two photons. These two photons are going to interact with two more neodymium ions in this upper laser level. Now how many two neodymium ions are coming down? How many photons now I am going to have? 4 photons in coherence. 4 photon in coherence. Means what happened to the these photons? Amplified, or their energy is decreased? They are amplified. Means their strength is increased. Okay, so amplification is taking place here. So this process, this amplification of photon continuously takes place until, so these photons have sufficient amount of energy to come out from the partially mirror. Once they are coming out from the partially mirror, they will come out like as a laser beam. Once they got sufficient amount of energy, these photons, once they got sufficient amount of energy, so to come out from the mirror, obviously they will come out from the partially coated mirror only. So they will come out from the partially coated mirror with high intense coherent directional beam of laser. Okay, coherent, intense and directional beam of laser. Okay, so they are having laser emission is going to take place. So these are the different applications of lasers. Ophthalmology means it is related to eye. Okay, skin cancer, oncology means skin cancer can be cured. Skin cancer can be cured with the help of ND-YAG laser. It is a 4-level laser. Compared to ruby laser, ND-YAG laser, both are solid state lasers only. ND-YAG laser, ruby laser, both are solid state only. So ruby laser is a 3-level laser, ND-YAG laser is a 4-level laser. So 3-level laser output is pulsed form. 4-level laser output is wave form, continuous wave form. So continuous wave form is more powerful. Compared to ruby laser, ND-YAG laser is more powerful. It is a 4-level laser. So 4-level, what is the importance of 4-level laser? It will maintain population inversion for more time. Okay, when it is able to maintain population inversion for more time, so lasing action will be of continuous waveform. Lasing output is continuous waveform. Okay, so that is ophthalmology means eye related surgeries can be done with the help of means detached retina can be reattached. If the retina having some disturbance in it, so we can attach in particular, we can fix the retina in a particular position with the help of lasers. Which laser that I am going to use? We are going to use ND-YAG laser, that is called ophthalmology. Skin cancer related issues can be cured with the help of ND-YAG laser. Next, visualization techniques in fluid dynamics. Okay, visualization, fluid dynamics, it is related to water and fluid dynamics. In that we can have some techniques, visualization techniques that can be done with the help of ND-YAG laser. Next, range finder, range designators. For example, whenever there is a war takes place between two countries, what happened? So the defense are going to find where the enemy's aircraft is present, how much range it is. We can find the range finder, range designators. We can find them, we can also destroy them with the help of lasers. Range, how much range it is there. Okay, what path it is coming, where it is coming, like that, which direction it is coming. Like that also we will find the location. Okay, so range finders and range laser designators can be done with the pumping tunable visible light lasers. So pumping purpose also we can. So for example, we can some lasing action can also be done with the help of lasers. Okay, so pumping means excitation of atoms from the lower energy level to higher energy levels. Up to now we studied about 2 types of pumpings. Okay, ruby laser we studied about xenon flash lamp. ND-YAG laser, now we are having one more, that is xenon flash lamp also we can use, krypton flash lamp also we can use. So that is optical pumping. Okay, sometimes we can use lasers for pumping also, for excitation of the atom. Okay, next research application. Okay, remote sensing, Raman spectroscopy, spectrometer. So what is see here? It is spectroscopy. Spectroscopy, absorption spectroscopy, emission spectroscopy. We know that when a radiation falls, what electromagnetic, light is nothing but what? Electromagnetic. It is a electromagnetic radiation. What is this? It is a electromagnetic. It is an electromagnetic radiation. When electromagnetic radiation means it is having electric field. What it is having? Electric field and magnetic field. So these two are perpendicular to each other. So this is from sun we are going to have electromagnetic radiation. So electromagnetic radiation means it includes X-rays, gamma rays, visible light, IR radiation, UV radiation, radio waves, all these things comes under electromagnetic spectrum. Means electric and magnetic field. So they are perpendicular to each other. So the radiation means electromagnetic radiation coming from the sun and interacting with the matter sample. So it means the radiation will be absorbed by this body and it will radiating the emission. It is giving some radiation. Some radiation is emitted from the body. So with the help of radiation, we are going to get different colors. Okay, the body is radiating different colors, mean different frequencies. When the body is radiating the radiation of different frequencies, we are going to get different colors. So we are going to get a different spectrum. We are getting the spectrum means of different colors. So this is emission spectrum. Next, absorption spectrum also will be there. So that is called spectroscopy. So spectroscopy experiments can also be done with the help of laser. Okay, so with the help of laser is a monochromatic, electromagnetic is polychromatic. Electromagnetic radiation is a polychromatic. So here laser is a monochromatic. So with the help of laser also we can do the spectroscopy. So it is incident, light is come out. Okay, so this is, it is emitting the photon. It is absorbing the photon and it is emitting the photon. Next, another laser is gas laser. Till now we discuss about two lasers, ruby laser, helium-neon laser. Sorry, ruby laser, Engg laser. Ruby laser is a solid state one, Engg also solid state one. Okay, so one is 3 level, one is 4 level. Okay, so that is a pulsed form and Engg is wave form. So that is weaker laser and it is stronger laser. So Engg laser is having more application than the ruby lasers. Okay, so here we are using elliptical shaped cavity. So what is the use of using elliptical shaped cavity? Because whatever the photon emitted from the one of the focal lengths where we kept a flash lamp, so the every light is going to be come towards the another focal length. Means every photon is going to be interacted with the neodymium ions. Okay, so that means no photon is going to be wasted here. Every photon is going to come to the another focal length after experiencing various reflection. Okay, finally it has to reach the another focal length. Okay, so from the ground state to 2 pump states we are having E4 and E5. So they won't stay for there more time. Now we are having upper laser level, lower laser level, and after that ground state. Okay, so helium-neon laser. So Ali Jawan developed this 1961. It is a gas laser. First gas laser demonstrated by Ali Jawan in the year of 1961. First gas laser. Okay, so it is a 4-level laser. What it is? 4 level. Whenever I said 4 level means immediately you have to recall that 4-level laser will give the output of continuous waveform. What is the waveform that you are going to get? Continuous waveform. Okay. Next, which technique we are using? Electric discharge pumping. So it is a 4-level laser. It is a not solid state one. It is a gas laser. What it is? It is not a solid state one. It is a gas laser. What it is? It is a gas laser. Which kind of pumping technique we are using? Electric discharge pumping technique is used. Which type of pumping technique is used? Electric discharge pumping means electrons are injected into the mixture of gases. What are helium-neon? Helium-neon are nothing but noble gases. Helium is a gas, neon also gas. We are going to use these gas molecules. Gas means noble gases. Okay, with the help of these gases, we are going to generate lasers. So that laser is called gas laser. The laser generated due to these gases, helium and neon. Okay, noble gases. So which type of laser it is? 4-level laser. And it is a gas laser, 4-level laser system. Okay, which kind of pumping technique is used here? We are using optical pumping like as ruby laser, like as Engg laser. We are using optical pumping. No, we are using electrical discharge. Means electrons are discharged into the mixture of these gases, helium and neon gases. So in this neon atoms are the active centers. In ruby lasers, who are the active centers? Chromium plus 3 ions. In ruby laser, who are the active centers? Chromium plus 3 ions in ruby laser. Okay, next in Nd plus 3 ions. Nd plus 3 ions in Engg laser. Now here, who are the active centers? Neon atoms. Who are active centers here? Neon atoms are the active center. Means active centers are nothing but they are the responsible for the lasing action. For whom? we are going to get the lasing action. Those ions or atoms are called active centers. They are the responsible for the lasing action. So who are the active centers here in this helium-neon? Neon atom. Sir, neon atom is the active center. What is the purpose of helium? Okay, so helium having is going to have two important nature. It is going to be interacted with the neon, that is the one thing, and it is having more energy absorber. It absorbs more energy. Okay, so whatever the heat is generated during the transition of lasing action, these helium ion are going to be absorb the energy. Not only they are absorbing that one energy, but also interacted with the neon atom for exciting them from lower energy level to higher energy level. For the excitation of neon atom, we are using helium atoms. So they are supporting character. In helium neon laser, helium atoms are playing supporting character to excite the neon atom, to achieve the more number of neon atoms in the metastable state. Okay, it is a 4-level laser. So now construction. So what is this? It is a tube, glass tube. Okay, so why we need this one? Because we have to enclose the mixture of gases. What we have to enclose? Mixture of gases, helium and neon gases. Okay, so we can't place them just like that because they are gases now. They will move here and there randomly. So they should be enclosed in a glass tube. Okay, so this is a glass tube having some dimension 15 to 80 centimeter length. Okay, so the either side of this one, the glass tube having so this you are having diameter is 11.5 centimeter. Now this side you are having one mirror, and other side what you are having? You are having one more mirror M2, mirror M1 and mirror M2. What is mirror M1? It is a 100% reflector. 100% reflector. Next M2, it is a partial reflector. What is this? Partial reflector. In that what we are having? Mixture of helium and neon. So after that we are going to have electrodes. What we are having? See, so these are the some atoms, helium atoms. Next these are the neon atom. So I have given some representation. They are the smaller size and they are the bigger size. Which atom is this one? It is a smaller size, means it is a helium. What is this? It is a bigger shape. So it is a neon atom. So I place more number of helium atoms than the neon atom. How much ratio they are going to be? 10:1. What is this? 10:1 ratio. So 10:1 means helium will be 10 number of atom, helium will be 10 and neon will be 1. Helium will be 10, neon will be . So these are the neon. See, this is helium atom and it is a neon atom. These are the electrodes. Now these electrodes are connected to radio frequency generator. So what it is? So this is electrode. Now we connected to radio frequency generator. Radio frequency, which generates some current, means which generates the electrons. These generated electrons are going to be injected into the mixture of helium neon gases. They are going to be injected into the helium neon gases. So once they are going to be injected into the helium neon gases, so what happened? First you have to achieve the population inversion, then some of the atoms will come down to the ground state, releasing the normal photon, and these normal photons are going to reflect with the mirrors and get back to the atoms present in the metastable state and causing them to ground state, means stimulated emission, and releasing the multiple photons. So multiple amplification of photon will take place. So see here how it will be taking place. So first what we are having, we have to need it is a glass tube. It is a glass tube. Okay, having some dimension. So in that gas tube, we are enclosing a gas of helium and neon. What is the gas? Helium and neon. And 10:1. 10:1. Okay. So the dimensions are scalable. It is not compulsory that it should have dimension 10 to 50 centimeter and having the 12 centimeters diameter. Length is 15 to 50 centimeter length, and the diameter is 12 centimeter length. It is some different, vary depending on the output laser, desired output, whatever the output that we want to get, depending on that we can change the dimensions also. First we are having a glass tube. That glass tube is enclosed with the two gases, helium and neon gases. These are the two noble gases. Helium having 10 atoms and neon is having 1 atom. 10:1 ratio. If it is 100, it will be 10. So like this 10:1 ratio, we enclose these atoms into the glass tube. Okay, and at around 1 torr pressure. So how much of pressure that we are enclosing this? Around 1 torr. So this pressure also depends on the output laser that we want to get. Okay, so we enclose these molecules into the glass tube. So this glass tube two side, what you are having? Two mirrors. What is this? It is a mirror M1, and another side what you are having? Mirror M2. So it is a M2. It is a 100% reflector, and it is partial reflector. It is a partial reflector. Means it less silver coated. So two mirrors will be there. Now we are having an arrangement of electrodes. What are these? These are the electrodes. These electrodes are connected to radio frequency. What is this? Radio frequency. Okay. So radio frequency generator. So this radio frequency generator will generate some amount of current. What it will generate? It will generate some amount of current. So current means electrons are injected. Electrons are injected into the mixture of these helium-neon gases. Now these electrons are going to have interaction with the helium and neon atom. So which atoms are going to excite? Helium or neon? Sir, the electrons which are ejected from the electrodes are going to have experience interaction with helium. This electron is going to be interacted with this helium atom. This electron also interacted with this neon atom. Now it is not going to show any partiality, because whatever the atom comes into its direction, means electron direction, it is going to collide with collide that atom and excite. But which atoms excite here? Neon atoms won't excite due to the collision of electrons. Only helium atoms only excite. Okay? Only helium. Why helium only exciting to the higher energy level? Because their mass number is, their size is very less. Light particles. They are light particles compared to that of neon atom. Neon are heavy particle, the bigger size. Helium are smaller size. And one more thing, you people are going to have a doubt. Sir, why they are in 10:1 ratio? Why more number of helium atoms? Why less number of neon atom? So why? Because so helium atoms are going to excite. See here. So this is helium atom. This is related to helium, and it is related to, I will show complete diagram here. See here. This is related to helium, and it is related to neon. Okay. So helium, more number of atoms are there. Helium, more number of atoms are there. So less, here neon atoms will be less. These are the neon atom. Okay. So what the energy is emitted from the electric discharge. So the electric discharge is exciting these neon atoms to the different energy levels. It is excited to helium-2 and helium-3. These are the excited levels of helium. Means these helium atoms are going to be excited to here, some of the helium atoms, and some of the helium atoms are excited to this level. Okay, this level. Okay, similarly the neon will having excited level. These are metastable state, neon 4 and neon 6. These are the excited levels of neon. So these are the excited levels. Excited levels of helium. These are metastable states. Metastable states. They are the metastable state. They are the metastable states of neon. Okay, neon 4, and one more state is there, neon 5, and here neon 4, so neon 3. Neon 3, next neon 2, next this is neon 1. Now see here, we have a glass tube, okay, quartz tube. The tube is enclosed with two gases, helium gas and neon gas. At what ratio? 10:1. And so what pressure we are using? Approximately 1 torr of pressure. 1 torr of pressure we are. So the two sides of the tube is having two mirrors. One is partial reflector, another side is full reflector. So that is the tube is having an arrangement called electrodes. That electrodes are connected to what? Radio frequency generator. So when we switch on the radio frequency generator, it generates the current, electrons. So these electrons are going to have experience collision with the helium atom and neon atoms. So helium atom is going to excite to helium ground state to helium 2 and helium 3. So there are more number of helium atoms are there in the ground state. So some of the helium atoms are excited to helium 2, some other remaining helium atoms are excited to another level, helium 3. Okay, neon also having, these are the metastable state, Ne4 and Ne6. So helium 2 and neon 4 are of same energy states, same energy levels. Similarly, helium 3 and neon 6 are of same energy levels, same energy states. Their energies are same. Okay. So what is that energy, you know? So it is around 20.61 electron volts. This is 19.81 electron volts. Ne4 having the energy of 19.81 electron volts, that is having 20.61 electron volts. So these helium 2 and neon 4 and helium 3 and neon 6 both are having same energy levels. Now these helium atoms excited due to the collision. These helium atoms are experience a collision with the electrons. These are helium atom. But these electrons cannot excite the neon atom because they are heavier. You can't excite the neon atom with the help of electron. Only electron excite the helium atom to the helium 2 and helium 3 levels. Okay. Now, what is the purpose of using more number here? What is the purpose of having more ratio of helium? They are 10:1, I said. They said 10:1. So out of most of the atoms, many number of atoms are going to come down to the ground state. These atoms, most of the atoms are going to come down to the ground state. Most of the atoms. So most of the atoms are reaches to the ground state. So they will going to all the other atoms are reached to the ground state. Here also all the other atoms are reached to the ground state. For example, here in helium 2, for example, 100 atoms are there. Out of 100, 90% are reached to the ground state. 90%. So 10%, 100 means 90 means 90 atoms. 10 atoms are stay in the helium 2 itself. Helium 2 itself. Similarly, helium 3 out of 100%, 90% will be come down spontaneously. Okay, so 10% will stay in that particular level only. So these atoms are going to stay. For that purpose only we are having more ratio of helium than the neon atom. So excited, no doubt they are excited to the higher energy levels, H3 and H2 levels. But these out of maximum atoms come down to the ground state. So few of the atoms only will stay there. Now these atoms, left out atoms in the helium 3, this helium 3 means having more energy layer. More energy, this will come down to the ground state, having the elastic collision. This helium atom will going to come down to the ground state and interacted with the neon atom. So this neon atom is going to be excited to which level? It is going to excited to this Ne6 level. What is that? Ne6 level. Similarly, the helium atoms, what are these? This helium atom which is present in He2. Why? It is coming down to the ground state, interacted with one more neon atom present in the ground state. So it will transfer, this helium atom will transfer the energy to the neon atoms and causing the excitation to the neon 4. This neon 4, this is a neon atom. Where this atom came from? It came from the ground state. Due to which helium atom? The helium atom present in the He2, it will come down and interacted with this neon atom and excited to neon 4 level. Similarly, the helium atom which is present in helium-3 will come down to the ground state, interacted with the neon atom and excited to neon 6. Okay, because these are the same energy levels. They are the same energy levels. So that this atom will excite the neon to this level. This atom will excite the neon to this level. That is the thing only. Okay, that is the excitation of neon atoms. So for that purpose only we use more number of helium atoms so that we can get more possibilities of interaction of neon atoms. We have to excite the neon atoms now. If you take less amount of ratio, so there is less possibility of interaction of neon atom. When less possibility is there, then the excitation of neon atoms will be less. So we can't get more population in this metastable state. In order to get more number of atoms in the metastable state, we use more ratio of helium atom. Okay, these neon atoms are going to be interact with the neon atom and exciting them to neon 4 and neon 6. They are metastable states of neon. Now they are going to come down to the ground, means different transition. So these neon atoms will come down. This neon atom will have transition from here. Okay, 3.39 micrometers. What is this? 3.39 micrometer. So one more transition we are going to have from this one to this one. So here we are having 628 angstrom wavelengths. That is laser. What is this? It is a laser. One more transition that we are having from here, 1.15 micrometer. Means there are 3 different transitions are taking place from the metastable states. What are the metastable states? Ne6 and Ne4. They are the metastable state. From that metastable state, 3 transitions. So what are the 3 transitions? I am going to explain here. See here. See, this is the diagram. So here helium atoms. These are the helium atom. These helium atoms will excite to this level. So this level, and also this helium atom will excite to this level. So the excitation, see one more time. See, this helium atom is exciting to helium-2 level. Because of what? Because of collision of electron. Sir, collision is taking place with the neon atom also kada. Neon atom also experiencing the collision of electron because they are also present in the tube. So why they are not getting excitation? Due to the collision of electron. As I told you, neon atoms are heavier than the helium atom. So the electron energy is not sufficient to cause the excitation of neon atom. No doubt they will have collision. But these helium atoms only excited to the different levels. Why they are different? Because the generator is not generating the same energy of electrons. It is not generating the same energy of electron. The electron with of lower energy will excite to lower excited level. The electron of higher energy will cause the helium atom to more higher energy level, excited level. So this helium atom exciting to this helium-2 level. So because of collision of electron, it is exciting. Next, this is one more helium atom. It is also going to be excited to another level, helium-3, due to the collision of electron. So, but these helium are not excited to neon 4 and neon 6, where these two are same energy states, same energy levels. These are two same energy levels. So whatever the energy, for example, 1.2 electron volt, it will be 1.2 electron volt. If it is 1 electron volts of energy, here also 1.8 electron volts of energy. Means helium-3 and neon 6 are of same energy states. Similarly, helium-2 and neon 4 are of same energy states. So if this level is having energy of 0.8 electron volt, this will be having a 0.8 electron volts. So they are same energy levels. So now the excitation of helium atom is over. Okay. Now most of the helium atoms, whatever the helium atoms are, most of the helium atom come down to here ground state. Most of the helium atoms are come down to the ground state. Okay. For that purpose only we maintain a ratio 10:1. Okay. So most of the atoms which are present in the excited states, helium-2 and helium-3 will come down to the ground state. So few atoms only left out. So this is the remaining helium atom. These are the remaining helium atom present in the excited level. For example, 10 atoms are there excited here, helium-3. 10 atoms are excited to helium-2. Out of 10, 9 are de-excited to ground state. Here from helium-2, 10 atoms are there. Out of 10, 9 atoms are de-excited to ground state. So how many atoms are present left out here? 1. Here how many? 1. Means most of the atoms are going to de-excite to the ground state. Okay, for that, so only few atoms only are going to have interaction with the elastic interaction with the neon atom present in the ground state. These atoms are going to, this which helium atom present in the helium-2 level. Which atom? Helium atom present in the helium-2 level, come down to the ground state, interacted with this is helium atom. What is this? Helium atom. Interact means transforming the energy to the neon atom. Okay, and exciting this neon atom to here. What is this? It is a neon atom. Okay, next, that is the thing. Similarly, it is one of the helium atom present in the helium-3 level, having more energy. Now this atom is going to come down to the ground state and interacted with this neon atom. Means this neon atom is transfer the energy and excite this neon atom to this level. Here what it is? It is a neon atom. So the excitation of neon atom is not due to the collision of electron, it is due to the collision of helium. So for that purpose only we are using the helium. So helium atoms are what? They are supporting character. They are supporting to excite the neon atoms to achieve the population inversion. So once we got more number of neon atom in this one, this is called metastable state. What it is? It is also metastable state. It is also metastable. So these are the, means neon 6 and neon 4 are the metastable state. Now what we are having? Neon 5. Next to neon 4. What is this? This is neon 4. Next to neon 3, neon 2 and neon. Now see here what happened. So once once the atoms are reached here, so few of the atoms are transition. This neon atom is transition from here. So here also one transition, here also one transition. Okay. So how many transitions that we are having? The transition of neon atom takes place from neon 6 to neon 5. Neon 6 to neon 5. Releasing the energy, how much? 3.39 micrometers, means 33,900 angstrom. One more transition, neon 6 to neon 6, this is neon 6, neon 6 to neon 3. What is this? Neon 6 to neon 3. Neon 6, this level to neon 3. How much of radiation we are getting? 6328 angstrom. How much? 6328 angstrom. One more transition also taking place from where? This is neon 4 to neon 3. What is this? Neon 4 to neon 3. So what is the energy that we are getting? 1.15 micrometer. 1.15 micrometer. So that is nothing but 11,500 angstrom. What is that? 11,500 angstrom. Means we are getting 3 different lasers of different wavelengths. So you know that this is a infrared region. What is this? 11,000 11,500 angstrom is IR radiation, infrared radiation. Means the transition from Ne4 to Ne3, infrared radiation. Similarly, the transition from Ne6 to Ne5, so that is also 33,900 angstrom. So that is also infrared. Both are infrared. But this one, what? The transition from neon 6 to neon 3. What is this neon 6 to neon 3? So that is 6328 angstroms. What is this? 632. So that is visible light. What is this? Visible light. red color. What is this? Red color. The transition of neon atom from Ne6 to Ne3, we are going to get a laser emission of red color. The other emissions comes under IR radiation, infrared radiation. So applications of helium-neon laser. Helium-neon lasers are low cost. They are low cost and simple to use. They are low cost and you can use simple. Okay. So why low cost? Because they are gases only. Helium and neon gases. Okay. And radio frequency. Pumping source also easily available. Pumping source also easily available. Gases also easily available. So the source required for the lasing actions are readily available. So they are low cost and simple to use. We can use simple to use. So compared to with other gases. So microscopy, spectroscopy application. Microscopy, spectroscopy application we can use. Barcode scanning. In generally you are seeing in shopping malls, in various places we are using the barcodes to read the data. Okay, for example, a book, when there is having a barcode on it, it is going to give the information. A chocolate, there is a barcode on it. So a garment, garment's necklace or what is it, there will be a barcode is there. So they are going to scan that one, it will give some complete data, how much weight it is, so how much wastage it is, okay, how much cost it is, okay, everything data is going to be present. So that the barcode can be read with the help of helium-neon lasers. So optical disc reading. So these are the things that we can do. Metrology and holography. Metrology, it is not meteorology, it is a metrology. It is related to measurements and their applications. Measurements means how much thickness it is having, how much width it is having without any physical contact. For example, in general we are going to use a tape or any measuring device to measure the distance, to measure the thickness, to measure the volume. So we are going to use some objects, we are going to use some equipment, but without any physical contact, with the help of lasers we can measure the things. So measuring technology, measuring technique is called metrology. Okay, and holography means three-dimensional photography. Holography means three-dimensional picture. So that can be formed, that can be read with the help of helium-neon laser. Helium-neon laser is a gas laser, 4-level laser. The output of the helium-neon laser is 6328 angstrom. There are 3 different transitions are there, different lasers. So in which 6328 angstrom is the helium-neon laser wavelength. That is also red color. So the output is continuous waveform. What is the waveform? Continuous waveform. So what is the ratio we have taken? 10:1 ratio. So what is the purpose of you having more number of helium atom? Because most of the helium atoms are going to de-excite to the ground state. Okay, so there is to increase the possibility of excitation of neon atom, we are using helium atom. So to excite more, we can add more helium atoms also in order to get more possibility of excitation of neon atom. So here we are just using 10:1 ratio. Okay. Next, this is optical disc reading. How laser reads the information. So we are having, see here, it is a arrangement. So that is a label. It is having metal reflector layer. It is a metal reflector layer and it is a label. So there is a pattern. You can see there is a pattern here. So here it is one pattern, here one pattern, here it is one pattern. So when laser comes here, when laser comes here, it comes here, so there won't be any reflection of light. When laser falls here, see here, when laser comes into depth, when laser enter into the depth, laser is moving, laser or disc is moving. When disc is moving, for example, when it is disc is moving, there is a pattern. There is a pattern, number of patterns are there. So when the pattern comes here, depth part, that laser will not experience any reflection. So there is no reflected light reaching the photoelectric cell. When there is no signal is reflected, means it studies as 0. When a laser is at a flat surface, when laser reaches to a flat surface, it reflects the light and the photoelectric cell read that information as 1. So the pattern, whatever the disc will have some patterns, depths and flat places, depth and flat places. Okay, so whenever the laser enters into the depth, so the light will not reflect from it. So the photoelectric cell will not reach any signal. So when it is not reaching signal means it reads as 0. Similarly, when the laser reaches to the flat surface, the light will reflect from it, and that reaches to the photoelectric cell. That photoelectric cell reads that as a 1. Okay, so that is the means it reading the binary information, zeros and ones. Who is doing this means information, reading the information? Helium-neon lasers. Which lasers that we are using? Helium-neon lasers only we are using to read this one. So this is barcode scanning. We know that barcode scanning means it is a laser source, it is a oscillating mirror, it reflected this oscillating mirror. From this oscillating mirror, when it is oscillating, it generates some different range of lasers, and it is a barcode. That light will come out to the barcode and reflected back, and this scanner, it is coming to the scanner. So reflect means when we can get the information. Simple question. When light falls on the object and reflect back, then only we come to know the information. Similarly, we are having a laser gun, barcode scanner. So there is a barcode, that is an image, and it is a barcode scanner. This barcode scanner is giving light. So this light is going to be fall on it, and it is going to reflect back on a cell. Okay, what it is? It is going to get on a sensor, which sends the electrical light signals. Which sense what it is sense? Light signal. So that light signal will convert into the electrical signal. So that is a barcode scanner. So which kind of laser that we are using here? Which laser here? It is a helium-neon laser only. For read the barcodes. To read the barcodes, we are using the helium-neon laser. So see here, metrology, just now I said. So this is a thickness. How we are finding the thickness? Without any physical quantity, contact. There is no physical contact. There is only contact of lasers only. So that will show the value, how much thickness it is having. So that without physical contact, we can measure the objects. That is called metrology. Okay, metrology is a science of measurements and their application. It is a science of measurements and their application is called metrology. Okay, so that can be done with the help of helium-neon lasers only. Next, another laser, semiconductor laser. What is this? Semiconductor laser. Another laser. At the beginning only I said there are three different types of lasers. Engg laser, helium-neon laser. Now we are entering into the semiconductor laser. So semiconductor laser means we know about p-type semiconductor and n-type semiconductor. So p means positive, n means negative. Means p is having more number of holes in it, n is having more number of electrons in it. Majority of electron in n-type semiconductor, majority of holes in the p-type semiconductor. So when we brought these two semiconductor into contact, then we will form a p-n junction diode. So that p-n junction diode can be used as a laser diode. Okay, we know that p-n junction diode can be used as a LED, p-n junction diode can be used as a laser diode, p-n junction diode can be used as a pin diode, p-n junction diode can be used as a photodiode, p-n junction diode can be used as a Zener diode. Okay, so that is the thing that we already know. Now what we are going to do with the help of p-n junction, we are going to construct a laser diode. Okay, so see here. There are two important criteria are there. To construct a semiconductor diode laser, there are two important. We can't use every semiconductor. Students, what are the semiconductors you know? Germanium, silicon. Okay, but one more semiconductor is also we are having, gallium arsenide. What is this? Gallium arsenide. That is the one more semiconductor. Okay, so we can't use any semiconductor just like that for the construction of a semiconductor laser. We can't use germanium and silicon diodes for the laser diode. Why? Their band gap is how much? 1.424 electron volts. That is 1.4, so not 4. Gallium arsenide band gap is 1.424 electron volts, whereas germanium is having very less. So this band gap only is suitable for the laser emission. This band gap only laser. Where when we use germanium and silicon, there also we are going to get, but we are getting phonon heat energy. Here we are getting photon when we are having this band gap. So see here, to construct a semiconductor diode laser, we have to satisfy two important criteria. Okay, so the material that we are using, the semiconductor that we are using here, it should be having direct band gap semiconductor. What it is? Direct band gap semiconductor. What is direct band gap? For example, here it is a conduction band. What it is? Conduction band. So what it is? Valence band. What it is? Valence band. So see here, it is momentum and it is energies. So there is energy and momentum. So the electron, what it is? Electron. And here what you are having? Hole. What you are having? Hole. So this electron and hole. This electron directly recombines with the hole. Which electron? The electron present in the bottom of the conduction band, the hole present in the top of the valence band interact directly. There won't be change of any momentum. So there is no change in the momentum. When there is no change in the momentum, means energy also no change. There is no change in the energy. So there is no change in the energy. So no energy is wasted. Okay, so the band gap should be of direct band gap semiconductor. Direct band gap semiconductor. So the best example of a direct band gap semiconductor is gallium arsenide. So first, what is the first criteria to construct a semiconductor laser? The material, the semiconductor material that we are using to construct a semiconductor laser should have direct band gap semiconductor. Should have direct band gap. The second one is degenerative semiconductors. What it is? Degenerative semiconductor. The material should be of direct band gap. The material should have, what is this? Direct band gap. Just now I said what is direct band gap. And the material should be degenerative. What is this? The degenerative. What is degenerative? Means it should have more number of doping. So doping should be of more charge carrier should be present. So how much the charge carrier should be of 10 to the power of 17 or 10 to the power of 19 dopants, means the trivalent. So to have a p-type semiconductor, what should we dope with? Trivalent or pentavalent? To get the p-type semiconductor, we should dope with trivalent impurity. The trivalent impurity means trivalent, third year group elements. So okay na? So how much of the impurity should be 10 to the power of 17 or 10 to the power of 19 amount per centimeter cube. Okay, that many number of trivalent are doped to the tetravalent. Then we will get a p-type semiconductor. What we are going to get? A p-type. Similarly, so n-type, how many impure dopants we should dope? 10 to the power of 17 or 10 to the power of 19. So to get n-type semiconductor, what should we dope with? We have to dope with which type of impurities? Pentavalent. When we doped with pentavalent impurities into the tetravalent, we will get n-type semiconductor. When we doped trivalent impurity into the tetravalent, we will get p-type. Means holes will be more here, electrons will be more there in n-type semiconductor. Means here heavily doped p-type, heavily doped n-type semiconductors should be contact. Then we will form a heavily doped p-n junction diode. Okay. See here. So one more thing, what is the important criteria? The material should be of, the semiconductor material should be of direct band gap semiconductor. Second one is the semiconductor should be of degenerative semiconductor, means should be doped with more impurities. Heavily doped semiconductors should be used. Okay na? So and the diode should be operated in forward bias. The diode should be operated in forward bias. So what happened when the diode is operated in forward bias? So these diode should be operated in forward bias. See here, when you are giving some forward voltage, what it is? Forward voltage. Here it is a forward voltage. Forward voltage. When we are giving forward voltage, what happened? These holes will drive towards the junction. Okay, and these electrons will drive towards the junction. So what happened? This electron will be, this is the electron, will recombine with the hole at the junction. Why they are moving towards the junction? Because the junction diode is connected in a forward bias. The forward potential will always drives the charge carriers present. So the holes present in P region towards the junction. The electrons present in the N region will drive towards the junction. So these charge carriers, majority charge carriers will come towards the junction. When they come towards the junction, what happened? They will recombine. So when they are recombined, what happened? They generate some photon, normal photon. Okay. So one more thing you have to remember. So here the junction is the active medium. Junction is called active medium. So the lasing action is going to take place at the junction. Junction is an active medium for semiconductor lasers. Okay. So here the electrons from N region and the holes from the P region will drive towards the junction, and they are going to have recombination. Here charge carrier recombination. What happened? Charge carrier recombination. 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 Whenever charge carrier recombination, you are going to get a photon. What you are going to get? A photon. Photon emission will be takes place. So this normal photon, what it is? A normal photon. So what it is going to do? So it is going to have reflections. Okay. So from the semiconductor is having how many sides? 4 sides are there. So junction sides. How many sides are there? Junction side. So in the from the 4 side, 2 sides are roughened. 2 sides are roughened, and remaining 2 sides, one side is finely polished, means finely silver coated, another one is partial coated, means one is finely coated, another one is partially coated. So from the partially coated, what happened? Lasing action will takes place. So at the junction, what happened? This photon want to come out from the junction. So yeah. This is hole, this is electron, this is hole. It is P type and it is N type, and it is connected in forward bias. Forward bias. So when this hole comes to here, similarly this electron will come here. So these two are recombined. So when they recombine, what you are getting? A photon. A photon. So this photon, so what happened? It tries to come out from the 2 sides. Out of 4 sides, 2 sides are roughened, closed. 2 sides are left. One side is acting like as a fully reflector, another side is acting like as a partial reflector, like as another lasers. 4 sides are there. Out of 4 sides, 2 sides are roughened. 2 sides are left now. These 2 sides, opposite sides. So one side is finely polished, another side is medium polished, means partially polished. Okay, this photon tries to come out from the partially coated mirror. So what happened? It won't come out from this one. So what happened? It is going to be interacted with another hole present in the depletion layer. So why? Because you are giving some forward voltage now. So more number of electrons and more number of holes will be come out. So this normal photon is going to create more stimulated photons. When you are getting more number of stimulated photons, what happened? You are going to amplification. You are going to get amplification of photons. So these are the things that are happening at the junctions only. Okay. Initially, we are getting ordinary photon. These ordinary photons, once again, what happened? They are going to generate stimulated emissions. They are going to have the stimulated emissions. Stimulated means they are going to interact with the another electrons. So when semiconductor lasers are in which bias? They are in forward bias. What happened? Holes and electrons are recombination takes place. What happened? In PN junction diode, what happened? Electrons and holes are recombination and produces photon emission. What they are producing? Photon, not phonon. Photon means light emission takes place. This emitted photon, whatever the normal photon is emitted in initial, this emitted photon, what happened? Stimulated further recombination. That further recombination, that photon, what it is giving, stimulating the other further recombination. Further recombination means, so this electron, this photon, for example, this photon, it tries to create a recombination of another electron hole recombination. This photon will create another recombination of the electron photon. So it is going to generate photons. So normally these are going to have recombination due to the forward voltage. It is going to generate the photon. This photon is stimulating the recombination of, so this means due to the forward voltage, normal photons are existing. And these photons are stimulating the another, what happened? Recombination. So that recombination also generates photon. So we are getting photons two ways. One is due to the recombination of electron and holes at the junction due to the forward voltage. That is the one thing. And another one is whenever the forward voltage recombines the electron holes, they are generating the photon. This photon is stimulating the other recombination. Okay, so this creating another recombination. Whenever recombination takes place, photon you are going to get. You are getting photons. So the generation of photon is going on increasing. Amplification, multiplication of photon emission takes place at the junction and produces the laser. That produces the lasers. That is the thing happens at the junction. So I would like to say simple diagram. This is P type, it is N type. So it is a depletion layer, forward bias. This hole moves towards the junction and it comes here. This is the electron which comes towards the junction. So this is the recombination. What happened? Recombination. What you are getting? A photon. Now this photon, what it is doing to, it is recombining the remaining electron holes. It is recombining the electron holes. So what happened? You are going to get photon. You are getting photon. So this is the one photon and it is one more photon. So like this, the emission of photon takes place not only due to the recombination of electron and holes due to the forward bias voltage, and also due to the photon emitted at the junction is also stimulating the other recombination. So that is also generating the photon. So photon, two photon, one more time. So four photons like this. What happened? Amplification of photon. So this until the amplification takes place, until these photons have sufficient amount of energy to come out from the one of the junction. So four sides are there now. Four sides, two sides are roughed, two sides, one is finely polished, one is partially. So from partially coated one, so the laser will come out. So this is what P plus. What is P plus? P plus is nothing but what? Heavily doped P-type semiconductor. N plus means what? Heavily doped N-type semiconductor. So semiconductors are two types. Semiconductors are two types, homojunction and heterojunction. Semiconductors are how many types? Two types. Homojunction. Next one is hetero. These are the two junction. Now I am going to explain about what is homojunction. Homo means same type of band gap. Homojunction means the semiconducting material have same band gap. Or the semiconductor material should be of same kind, should be of same kind, same type. Same means that the p-type semiconductor what we are having, n-type semiconductor should be of same material. Whatever the p material is there, n-type material should be of. Sir, when p-type is having same material, n-type is having same material, how come they will be p-type and n-type semiconductor? Either they will be p or they will be n. So listen my student, no doubt p-type material is of same kind, n-type material is also same kind. Okay, so but the dopants are different. One is doped with trivalent, another one is doped with pentavalent. The one which is doped with trivalent, it will become p-type. The one which is doped with pentavalent, it will become n-type. But the parent material is same. The parent material is same. So such kind of band gap semiconductor is called homojunction semiconductor. Means when we are using a same kind of material for the p-type semiconductor and n-type semiconductor forms a p-n junction, then such kind of semiconductor is called homojunction. Homo means the name itself, homo means same kind of materials are come together forms a junction. So that is called homojunction semiconductor. So one more thing also you can say, the material with a same band gap semiconductors also called homojunction semiconductor. For example, which kind of material is suitable for here? I already told you gallium arsenide. Okay, na? Gallium arsenide is material. Now I am going to use same kind of p-type. This is what? It is a p-type. What it is? Gallium arsenide. So it is p-type, means it is doped with trivalent. Trivalent means valency 3. Now you are going to have holes in it. What you are going to have? Holes in it. Now what I am having? Another same material I have to use. It is also gallium arsenide. As I said, the p-type material should be of same kind, n-type material should be of same kind. Okay, and but how it will become p, how it will become n? Because it is doped with trivalent, you will have more number of holes. When you doped with pentavalent, what it is? Pentavalent, it will become more number of electrons in it. You will have more number of. So it is n-type. What it is? N-type. So when they are brought into contact, it is called junction. What it is? Junction. So junction is nothing, active medium, active layer. Okay, that is active medium. So whatever the lasing action is taking place through the junction only, through the junction only. So homojunction means when we use same band gap semiconductors to form a junction, then such kind of junction, that kind of semiconductor laser is called homojunction semiconductor. Or another thing, same band gap semiconductors are used as for p-type and n-type semiconductor, that is also called homojunction semiconductor. So what happened exactly here? What happened exactly here? So we know that it is a p-type region. What you are having? It is a p-type and it is a n-type. So when p-type and n-type, it is called junction. The gap between them two is called a junction. Okay. So when there is no bias, means forward bias, no external forward voltage, there won't be any charge carriers present at the depletion layer. There won't be any charge carriers in the junction. Okay, when there is no bias means no forward voltage. No forward voltage, no charge carriers will be at the junction. When we are giving the forward voltage slowly increases, what happened? So the electrons from the N region are pushing towards the junction, the holes from the P regions are pushing towards the junction. So they are entering into the junction. So when they are entering into the junction, what happened? They will recombine to each other. So here what happened? This hole is recombining with this electron at the junction. This hole and electrons are recombining at the junction. Okay, so that results what happened? A normal photon. This photon, what it is doing? It is stimulating the it is stimulating for the further recombination. It is stimulating further recombination of electrons and holes at the junction. Whenever it is doing further stimulation of further other recombination, so that is going to generate photons. Okay, so photons are generating due to the recombination of electron and holes at the junction due to forward voltage. I repeat, the generation of photon emission takes place at the junction due to the recombination of electrons with the holes at the junction due to forward voltage. And next generation is due to these generated photon will stimulating the other photons. Okay, recombining the other electron and hole pair, generating the photon. So it's like this we are generating photons in multiple way. So this multiplication of photon is going to increase the power, means amplification of the photon. Once these photons are getting sufficient amount of energy, they will come out from the junction as a laser. They will come out from the junction as a laser. It is not a junction. So here they will come like as a laser. So this energy gap means it is a conduction band, bottom of the conduction band, and it is a top of the valence band. The gap between these two is called energy gap. Okay, na? And here also, so what we are having, see here, it is a bottom of the valence band and top of the valence band. So that gap is called energy gap. This gap is called energy gap. So whatever the energy gap, for example, X here, so the energy gap here, sorry, this is the gap. This gap is called energy gap for N type. For example, energy gap is X. Here, this energy gap is X. Means P is having energy gap, the P material having what energy gap? X. So for example, we'll just take 1.4 electron volts. Next, N-type material also having same X. How much? 1.4 electron volts. So the P material having same energy gap, N material also having same energy gap. So the junction formed due to this one is called homojunction. That is called homojunction. So same band gap materials are used for the construction of a junction, that is called homojunction. Like that also you can say. Or same materials are used for P-type and type and forms a junction, that is also called homojunction. Okay, so that is a homojunction. So the laser emission takes place. So lasers, why we are semiconductors, lasers are very important. Why? Because they are easy to operate. They are easy to operate. Okay, and they can easy to we can construct easily. They are readily available, cheaper in cost. Okay, so the operation of using of lasers also very easy. We can move them easily from one place to another place. Okay, they are small and compact, smaller in size, compact in size, easy to operate, user friendly, and we can get different ranges of wavelengths, lasers. So the output of semiconductor laser, either you can get pulsed mode, you can get in a continuous waveform. So two waves we can get, either you can get pulsed mode, you can get a continuous waveform. So two kinds of, so that is the main advantage of semiconductor laser. But there are some drawbacks are there in the case of homojunction. Homojunction means what is the main drawback of a homojunction? More divergence. Whatever the laser emitted, for example, so this is the junction, say here. It is a P-type, it is a N-type. So whatever the laser is emitting here from the junction, it is having more divergence. Means it doesn't maintain unidirectionality for a longer time. It loses its directions. So divergence is less, means it is having, it is spreading more. So when it spreads more, what happens? It loses its power. And one more main disadvantage is its threshold current density is more. Means the amount of current that we have to flow through the junction in the forward bias. So we know that we have to give some forward bias now. P-type, N-type. We have to give forward voltage. So to drive these holes from P region to towards junction, these electrons towards this region. Okay, so to drive we have to recombine more number of electron and holes at the junction. So threshold current density is very high. So that it is not means it required more forward voltage to recombine the electron and holes. When you are going on increasing the forward voltage, there is a chance of damage of diode. Means the diode will break down. Means it will burn because of high amount of threshold current density we are using in order to get the recombination of electron and holes to get the lasing action. So we can't use the laser diode, homojunction laser diode continuously for a longer time. You can use for a limited amount of time only. For longer time we can't use because there is a chance of breakage of diode. Why? We need more threshold current density, more recombination should be required. So more current has to be flow through the diode. So in order to get more recombination. Okay, so that is the main drawback. So how much of 400 ampere per millimeter square, that is the threshold current density. Okay, so I'm going to draw threshold current density. Which type of laser emission we are getting in the homojunction? Pulsed mode. Which type of? Pulsed mode. Pulsed mode means what happened? On and off, on and off. Laser is not coming. So this is a photo, laser emission stops. Laser emission stops. Laser emission stops. Okay, there is a time delay between one laser emission to another laser. The laser is not continuously emitted. So there is a discontinuity in the laser. Means pulsed form of laser we are going to get in the case of homojunction laser. Okay, so the output has a laser beam large divergence. When you are having more divergence, the power will be decreases. See here, for example, see here, for example, this is a laser. This is less divergence from the initial place to when it reaches to the destination. Degree of divergence is very less. Degree of divergence is very less. When you are having more divergence, what happened? When you are having more divergence, what happened? So it loses its power. When light is diverged from its direction of propagation, it loses its power. Okay, so the more number of lasers, more number of photons will not have coherence. More number of photons which are emitted from the junction will not have coherence. When they are not in coherence, what happened? The amplitude will not be magnified. The amplitude, resultant amplitude of the waves will not be magnitude, means amplified. When amplitude is not magnified, means what happened? Increased intensity will not be increased. Intensity is not increasing, means the power is loses. So homojunction lasers are having more degree of more divergence. That is a drawback. Means the power is not that much enough. Power is less power lasers we are going to get. Okay, poor coherence. Coherence will not be there. Means they will not maintain a constant phase difference. The emitted photons will not maintain the constant phase difference for a longer times. Means poor coherence and also poor stability. So they won't direct in one particular direction. The stability will not be the same. It is having poor stability. Next, heterojunction semiconductor. The name itself is saying heterojunction. Means here the PN junction is going to form due to the adding of, means joining of a p-type material, n-type material. But the materials are of different types. Unlike homojunction, the p-type material, n-type material of same kind and forms a junction. Heterojunction, the p-type material is different, n-type material is different. Okay, so when we are using such kind of material and forms a junction, that such kind of semiconductor is called heterojunction semiconductor laser. Homojunction semiconductor laser and heterojunction semiconductor laser. Homojunction means same kind of materials are used. Heterojunction means different kinds of semiconductor materials are used. Or you can give another statement, the materials are of different band gap. For example, we are having gallium arsenide, and they should be of direct band gap. Condition should not, that should be direct band gap semiconductor only. Okay, so what is a band gap? It is a conduction band and it is a valence band. So the band gap, for example, here is equal to how much you are having 1.48 electron volts. Now, for example, one element, some X material. Now I am using another material. So this is a conduction band. Next it is a valence band. Okay, so that is also direct band gap only. So this is band gap. This band gap is how much now? We are using 1.8 electron volts. What is that? 1 band. So this material having a band gap of 1.48 electron volt. This material is of having 1.8 electron volts. Means the band gap is of different. This material having band gap this much, and this material having another band gap. So when we use these two kind of materials to form a junction, so such kind of junction diode laser is called heterojunction laser, because we are using different band gap semiconductors. Okay, so that is called heterojunction semiconductor. So if the junction is made up of different types, means different band gap semiconductor materials is known as heterojunction. Simple. The materials are of different types. They are of different types. Band gap is of different. The junction is made up of different band gap. So then it is called heterojunction semiconductor. So here it is a heterojunction. We are having gallium arsenide p-type, gallium aluminum arsenide p-type, gallium arsenide p-type. So these are the different types of semiconductors are contact into each other. Then we will form a heterojunction semiconductor. The rest of the thing, the activity will be the same like as a homojunction. So we have to give some forward voltage here also. Here also recombination will take place at the junction. So here recombination results emission of photon. So this photon, emitted photon, they are going to stimulate the other recombination of electron and holes, so that they are generating the photon. So like this photons are multiplication of photon takes place. So multiplication of photon means the enhancement of the energy of the photon. So these photons are going on multiplied. Okay, so they try to come out from the partially coated mirror. So if they are not able to come out, means they are going to have one more time of interaction. Okay, they will generate the stimulated. They are going to create other recombination. So they are creating other recombination, producing the emission of photons. So the amplification of photon is going on continuously takes place until they get sufficient amount of energy to come out from the partially coated mirror, partially coated side of the junction. So once they got sufficient energy, they will come out from the junction with high amount of energy. High coherent unidirection means unidirectional monochromatic beam of light will come out from the junction. That is called laser. So this is possible. This is done with the help of two types of junctions, homojunctions and heterojunction. Homojunction output is pulsed form, more divergence, because of more divergence, less coherence, less stability, and they required more threshold current density. They required more threshold current density means the current density at which current starts flow, means spontaneous emission converted into stimulated emission. Okay, now spontaneous emission is going to convert it as stimulated emission. So stimulated emission means you will get more amount of photon emission, photon intensity will be there. Okay, so where you are going to get more stimulated means conversion of spontaneous to stimulated means at particular forward current it is going to happen, means that is called threshold current density, the minimum current density where we are going to get a stimulated transition starts. Okay, so when we are getting stimulated transition, then only we are going to get lasers. So homojunction semiconductor lasers required more threshold current density. So what is that? Just now we discuss, see here. So 400 amperes per millimeter square, that much of energy is required. Okay, so they are pulsed mode, they are going. Now heterojunction are powerful. Heterojunctions are powerful. They are having less divergence, and so that less divergence they were going to get a more coherent beam of light, more directionality they will have. Okay, more stability they will be having. Okay, the output will be more. We will get 10. How much of volt output we are going to get? 10 megawatts. How much? 10 megawatts of output laser we will get at this much of current only, 500 milliamperes of current, forward current that we are doing. Forward voltage means it will produce forward current. How much of current do you have to give to get this 10 megawatts of output laser? Just 500 milliamperes of current is enough to get this much of power output, 10 megawatts, huge amount of power that is. So it is not possible in the case of homojunction. and it can be operated. Threshold current density is very less. What about homojunction? 400. Now how much of current density? Very simple, 10 amperes per millimeter square of current density is enough to get this lasing action. Okay, so here continuous waves are going to produce. Okay, so the laser is of coherent and more monochromatic. They are monochromatic in nature. So that is the difference between homojunction and head. So these are the different semiconductors. These are what? Different semiconductors. This semiconductor, when you are using gallium arsenide, you will get the lasers of this much wavelength. Means which color they are? Red color. So what kind of application we are having? Laser pointers. What kind of application we are having? Laser pointers. Next, when you are using gallium nitrate or indium gallium nitrate, then what kind of application we will have? Which application? These are the wavelengths we are going to get when we use this kind of semiconductor. So one more thing you have to remember, gallium arsenide is not the one who have direct band gap. Whether you have to construct homojunction or heterojunction, the semiconductor material should be of direct band gap only. So what is direct band gap? You already know. Gallium arsenide also you can use gallium nitrate also you can use, indium gallium nitrate also you can use. So these are the different combinations of direct band gap semiconductor. When we use this combination of semiconductor, we are going to get the wavelengths of this one. So what is the purpose of this one? Data storage. Means in that CDs we are storing the information. So that information can be stored with the help of this kind of semiconductor lasers. For example, this is another kind. So this is the wavelength for pumping, for the excitation of ions from lower energy level to higher energy level in order to get the stimulated in order to get the population inversion. Pumping is used to get the population inversion. So I said earlier, some lasers also used for the to get the population inversion. Okay, so these are the one more laser. These are the different semiconductor lasers, semiconductor material. These are the different semiconducting materials. So they will generate different wavelengths. These different wavelengths can be used in different various applications in various fields. Okay. So some applications in medicine. So here there normal veins. You are having normal veins here. So this is a normal vein. So there is a various veins. There is a swelling here. There are veins swell. So there is a blockage in the veins. So that blockage can be removed with the help of lasers. Okay. So that can be done. For example, say removal of tumors. For example, cancer related tumors or brain tumors are there. So that can be used a laser ablation probe. A probe is inserted at that particular area where the tumor is present. Where the tumor is present at that particular area, a probe is inserted with that probe. So the laser is going to be destroyed that tumor, remove the tumor in that particular size only. Where the tumor is spread up to that area only, it will remove. So that tumor removal of tumors can be done with the help of lasers. Okay, which laser? This is the application in medicine. Here, kidney stone removal. You know, this is the familiar one. Nowadays, they are removing kidney stones with the help of lasers. So they are injecting with the laser gun. Okay, so through the veins and at that particular area where the stones are stuck, where the stones are present, and they are blasting that stones with the help of laser beam. So when they blast, then the pieces of stones will be removed from that particular place where they are present. So that can be done with the help of lasers. Okay, so removal of kidney stones can be done with the help of lasers. Next, the more important application of laser is in communication. Lasers are widely used in communication. Optical fiber communication, we are using lasers only. Okay, so in that visible range lasers we are having, infrared regions also we are having. Some type of lasers can be used with the help of visible wavelength light. Some other communication also can be done with the help of infrared wavelength laser light. Optical fiber, we are using lasers. Lasers are of two ranges. They may be in the infrared region, they may be in visible range. Okay, so infrared range wavelength lasers are using some other application. Visible range wavelength lasers are there, they will be used in another applications. We can use laser in optical fiber communication. The most important application of laser is in communication. So see, this is a communication. So it is a satellite. So we are having a transmitter and we are going to have a receiver. So it is going to send the information. So and transmit it and receive it. This information can be done with the help of without any physical contact. So that physical contact is nothing but laser only. The contact which is present between the transmitter and the satellite and transmitter and the receiver is with only lasers. So what we are having, transmitter and receiver, in between what we are having, optical fiber cable. Through that optical fiber cable we are transmitting the information in the form of light. What is the light? Lasers. Lasers we are using to transmit the information from transmitter to receiver. So optical form of data. Optical means light. Which light here? Lasers. Lasers are using to transmit from transmitter to receiver. So information is in the form of laser. So it means optical form. So these are the different types of, these are the fluorescent, means they are, it is also optical fiber related. Okay. Next, these are the, in chemistry, laser ablation synthesis we can do. So fine carving, we can get the design. Whatever the design that we want to get, that can, the design can be achieved with the help of laser. With the other instruments, other mechanical instruments, we can't do, we can't get a precise carving. We can get that precise carving with the help of laser. So these are the more surface modification. For example, in the device is there is a surface damage, surface imperfections is there. So that can be done with the help of laser. Surface modification done with the help of laser. Micro patterning. Micro means we can see some labels or pattern labeled on the objects or on the notebooks. So that patterning can be done with the help of micro, means smaller size. We can't see that much easily. Smaller micro patterning can be done with the help of lasers. So these are the various applications of laser in various fields. So I think everyone you understood. So today in my class what I explained? Different types of laser. First one I started with which laser? Solid state laser. Which laser? That is ND-YAG laser. Neodymium doped laser. Where it is doped? In yttrium aluminum garnet. Means aluminum. Few of the aluminums are replaced with neodymium ions. Okay. So that is there. So that neodymium is placed where? Elliptical shaped cavity. Okay. So what is the main advantage of elliptical shaped cavity? So whatever the light, it is having two focal lengths, in which I placed one focal length, one light source at one focal length, another focal length I place a rod, okay, and two sides we are having mirror. So what is the advantage of elliptical shaped cavity? So whatever the light is emitted from one of the focal length has to reach the another focal length, means no light is going to, no photon is going to be wasted. Every photon has to be reached to the another focal length where we place the ND-YAG rod. Okay, so every photon is interacted with the neodymium ions. Okay, na? So that is a 4-level laser. Okay, 4-level laser. So what is the output of ND-YAG laser? That is 1.06, 10,600 angstrom. That is infrared region. What is it? Infrared region. It is a 4-level laser. Means continuous output we are going to get. That is a continuous output. Next, after that I discuss about an ND-YAG laser. After that, helium-neon laser. That is a gas laser. Noble gases are used. So that are enclosed in a tube, glass tube, with a ratio 10:1, with some 1 torr of pressure. Two sides we are having mirrors. Which kind of pumping mechanism we are using? In ND-YAG, which kind of pumping? Optical pumping. Whether we can use xenon flash lamp or krypton. But in the case of helium-neon laser, which kind of pumping mechanism we are using? We are using electric discharge. Okay, with the help of radio frequency. So these electrons are collide with helium and neon, but they can't excite the neon because they are heavier. Helium are light particles, so they excited to helium-2 and helium-3. What are the metastable states of neon? Neon-4 and neon-6 are having same energy states as helium-2 and helium-3. Okay, so why we are using 10:1 ratio, more number? So we know that the more number of atoms are coming down ground state, few atoms only are possible to have the interaction with the neon atom, ground state neon atom to excite. So that we are taking more number of helium atoms. So that is output. 3 types of transitions are there. Helium-6 to helium-5, helium-6 to helium-3, neon-6 to neon-5, neon-6 to neon-3. Similarly, neon-4 to neon-3. 3 types of transitions are there. In one transition we got
1.15 micrometer. In one transition we got 3.39 micrometer. In one transition we got 6328 angstroms. Okay, so 6328 angstrom is visible range. The other ranges are infrared regions. Next we discuss semiconductor laser in that homojunction, heterojunction. What is homojunction? What is heterojunction? So heterojunction is having more advantages than the homojunction. So I hope you people understood. So thank you very much. Happy learning.